Hello, everybody, and welcome to this final plenary session of the AAS meeting on number 236. My name is Michael Strauss. I am Senior Vice President of the American Astronomical Society. I have the honor of introducing the plenary talk of Professor Christy Tremonti of the University of Wisconsin-Madison. Christy has made major and significant contributions to our understanding of galaxy evolution, with a particular focus on the relationship between and dynamics of the gas and stars in outflows, and how star formation rates depend on the physical properties of galaxies. While she was still a graduate student, she wrote a now classic paper demonstrating the relationship between galaxy metallicity and stellar mass, a result that has remained core to our modern understanding of galaxy evolution. She tells me that this paper wasn't even her main thesis, but rather was a side project. And according to Google Scholar, it has now received over 3,000 citations. Christy obtained her PhD at Johns Hopkins University and had postdoctoral positions at the University of Arizona and the Max Planck Institute of Astrophysics in Garching before becoming a faculty member in Madison, where she is now. In recognition of her research and teaching, she was just awarded the H.A. Romness Faculty Fellowship at the University of Wisconsin. The title of Christy's talk today is Gone with the Galactic Wind, How Feedback from Massive Stars and Supernovae Shapes Galaxy Evolution. Welcome, Christy. Christy, I think you need to unmute yourself.
All right, can you hear me now?
Yes, you don't have your camera on, I will also point out.
All right, I think perhaps you guys are controlling
You are all set.
I'm all set. All right. Well, thank you very much for your kind introduction. It's a great pleasure to be giving this talk. I very much was hoping that after this talk, we could all stroll outside and enjoy lovely downtown Madison. That is not to be this year, but I very much hope that you will come and visit us. Before that happens, things need to get back to normal. But I hope that when they get back to normal, it's going to be a new normal that reflects a more just and equitable society. So I encourage all of us to get out there and work towards that goal. Okay, so the focus of this talk, and let's see, I am now having trouble advancing my slides, unfortunately. I'm gonna have to exit my screen share and maybe restart because it is not letting me advance my slides.
Sometimes you, instead of clicking an arrow key,
okay,
just
here we
hit the
go.
space button, we'll do it.
I think we're good now. Sorry for the technical difficulties. Okay, so the focus of this talk is going to be on feedback.
Sorry, now we don't see your slides at all.
Oh, you don't? Interesting. All right. Let's see what we can do about this.
Yeah, you'll have to hit that share screen again.
All right. Sorry about the technical difficulties. Okay, do you see my screen now?
Yes, we do.
Good.
All right, take two. So the focus of this talk is going to be on feedback. And when we think about feedback in the context of galaxy evolution, we're almost always talking about negative feedback. So feedback refers to the idea, to the process by which stars and black holes return energy to the surrounding interstellar medium. And by doing so, they inhibit further star formation or black hole accretion. So black hole feedback is a topic that deserves a talk of its own. So I'm going to focus almost exclusively here on star formation feedback. And we can see a lovely small scale example of feedback in the star cluster, NGC 602. And we see these hot young massive stars, and we can see that they've clearly kind of evacuated this cavity around them. And they're blowing away that gas and preventing star formation in their immediate vicinity. So that's a kind of small scale example of feedback. I want us to think about feedback, feedback's kind of largest and most important manifestation. And that is what we call a galactic wind. So this is a bipolar flow of gas, dust, and metals out of the nuclei of galaxies. And our most beautiful example of a galactic wind comes from a nearby galaxy, Messier 82, shown here in a color composite made from our great observatories. We have a Hubble image showing the starlight. In X-rays, we see this blue volume-filling gas here that's coming out of the center of the sort of nozzle of the center of the galaxy. And then we see cooler entrained material shown in this image from Spitzer that's being carried along with this hot flow. And we'll talk about this in a little bit more detail, but this is the picture I want you to have in your head. A bipolar ejection of multi-phase gas powered by this energy return from massive stars. Okay, so to give you a sense of where we're going to spend a little bit of time talking about why star formation feedback is so critically important to galaxy evolution. And then we'll talk about how this feedback process actually works, and what a galactic wind is and where and when they occur. And we'll come back to some of the big questions that observers and theorists are wrestling with today, and we'll finish up by thinking about what the future holds. All right, so why is feedback so important? Well, to answer this question, cosmological simulations are extremely useful because unlike in our real universe, we can actually turn feedback on and off and look at how it affects things. So this is an example from some simulations by Dylan Nelson. On the top, you can see a simulation run without feedback, and on the bottom, we see a simulation where a feedback prescription has been included. And we're looking at the gas density, the gas temperature, and the gas velocity structure on fairly large scales. So I think this white circle here is the virial radius. So the key takeaway point here is simply that the universe looks pretty different when we have feedback and when we don't. And we'll try to unpack that a little bit. So the most important effect of star formation feedback is that it slows down star formation. So this is an earlier simulation from Hopkins, Murray, and Crowder, where they looked at 4 individual galaxies, one Milky Way-like galaxy, one high redshift galaxy, an SBC-like spiral, and an SMC-like dwarf. And again, they ran their simulations with and without feedback. In every case, when they didn't include feedback, star formation rates rose dramatically to exceptionally high values, and then they plummeted as the gas started to be exhausted. When feedback's included, there's a much more gradual rise, and then the galaxy ends up kind of self-regulating and keeping a roughly constant star formation rate. Now, this has a profound impact on the cosmic star formation rate history. So when we look at the star formation rate density of the universe, shown on the y-axis as a function of redshift, this is strongly impacted by this feedback process. So this is a different simulation, and this orange line here shows the simulation where no feedback was included. And in fact, it went off the plot. I had to fill it in with this dashed line here because it was so extreme. And the other colored lines show some different feedback implementations. Now, this simulation includes both star formation feedback and black hole feedback. This green run here includes star formation feedback, but no black hole feedback. And we can see that the inclusion or not of black hole feedback has a much smaller impact on the star formation rate density of the universe than star formation feedback. All right, well, not surprisingly, because feedback influences the star formation rate, it also sets the relationship between a galaxy's stellar mass and its halo mass, or dark matter mass. And we can see this example from a simulation here. If we want to quantify this, this plot now shows the ratio of stellar mass to halo mass as a function of dark matter halo mass. And if our universe was really simple, we might have thought that, galaxies would have stellar mass to halo mass ratios that were consistent with the cosmic average ratio of baryons to dark matter. And that's the dashed line here. But our universe isn't quite that simple. Observations tell us that the stellar mass halo mass relation has a distinct shape outlined here in gray from our observational data. When we don't include feedback, our simulations come pretty close to getting this cosmic average ratio, But we don't see this dramatic drop for low redshift or low mass galaxies. When feedback is included and these simulations show different ways of including the feedback process, we can reproduce the observations. Now, these simulations didn't go to high galaxy masses because in this regime, AGN feedback starts becoming important. But for galaxies with a mass comparable to the Milky Way or less, star formation feedback is really what sets this relationship. And it's really the ability of galactic winds to remove baryons from these low mass halos that establishes this. All right, well, feedback, as it turns out, also impacts galaxy morphologies. Without feedback, a lot of star formation happens very early on, so that by the time galaxies experience their first major merger, they're already pretty stellar-dominated systems. When stellar-dominated systems merge, they create dynamically hot remnants, so we get, spheroidal galaxies or galaxies with dominant bulge components. And you see that here in the simulation at the left. When feedback is included, and this shows two different ways of including feedback, we're able to reproduce galaxies in the local universe that still have thin disks, and that's very important. All right, last but not least, we really need feedback to remove metals from galaxy disks and produce the enrichment that we see in the circum-galactic and intergalactic medium, the regions outside and around galaxies. So this is the relationship that I worked on for my thesis between galaxy stellar mass and gas phase metallicity. And we see that there's a very distinct trend here that is evident over many, many orders of magnitude in terms of galaxy stellar mass. So this is a pretty dramatic correlation imprinted on the galaxy population. Now, not all of this correlation is due to feedback. We also know that low mass galaxies are gas rich, but even when we account for that fact, we see that we really need feedback to remove metals from low mass halos. We also see a lot of metals outside of galaxies, in the circumgalactic medium especially, and simulations tell us that those metals are driven out of galaxy disks in outflows. So this simulation here is color-coded by metallicity, and we essentially see those metals leaving along the minor axis of this galaxy and spurting out into the circumgalactic medium. So I hope I've convinced you that feedback is really important because it influences star formation rates, stellar masses, morphologies, and the chemistry of the ISM and the CGM. Now I'd like us to think about what the actual physics of the feedback process is. So feedback is actually not a single physical process, but it's really results from a combination of several different physical processes that operate on different spatial and temporal scales. And we're going to step through each of these and think about what their relevance and impact is. So the first one, and this is the one you probably had in your heads already, is supernova. When massive stars explode as core collapse supernova, they release 10 to the 51 ergs of energy into the surrounding interstellar medium. So originally you have that, ejecta blasting out of the supernova. That's going to thermalize and create a very hot, about 10 to the 8 Kelvin, overpressured bubble of supernova ejecta that's going to continue to expand and sweep up ambient gas. And this is a lovely image of a star-forming region in the Large Magellanic Cloud, where we see a supernova remnant here, but over here we see a larger area that's been designated as a superbubble. And this is a region where we've probably had multiple supernova explosions happening and contributing to the feedback process. All right, so most people would have had in their heads that, supernova might be a source of feedback energy. After all, they are giant explosions. The one that most people don't think of is stellar winds. We know O and B stars produce powerful line-driven stellar winds. They lose a tremendous amount of mass over their lifetimes. And this material streaming off of stars actually drives shocks into the surrounding interstellar medium. This is a beautiful example here. We see a wind from LL Orionis coming off and producing this little bow shock around this nearby star-forming cloud. So it turns out that stellar winds contribute as much energy and momentum as supernova. Yet for a while, they were kind of ignored. The other thing that makes them important is that, as soon as you have a star, a massive O and B star, you have a stellar wind. Whereas the supernova don't explode for, a few millions of years or a few hundreds of millions of years, depending on the mass of the star. So this is a very prompt form of feedback, and that turns out to be important. All right, so those O and B stars are also putting out a tremendous amount of light, primarily in the ultraviolet. And dust grains are fantastic at absorbing UV light. And it turns out this is another source of feedback, radiation pressure on dust grains. So the way this works is that O and B stars are shining some light. It gets absorbed by a dust grain. Sorry for my cartoon dust grain here. Things are definitely not to scale, but that dust grain is going to absorb the UV light and re-radiate it isotropically in the infrared. The trouble is that this light coming in carried some momentum. And when that light gets re-radiated isotropically, momentum needs to be conserved. And in order for that to happen, the cloud itself, or not the cloud, the dust grain has to move. And the dust is kind of coupled to the rest of the interstellar medium. So radiation pressure on dust can be a way of dragging that interstellar medium out and away from those O and B stars. This turns out to be particularly important in regions that are really dense and dusty, like the centers of ultraluminous infrared galaxies in the nearby universe. Another source of feedback that we have often not considered is photoionization. So we know that these O and B stars have a lot of ionizing radiation, but most of those photons aren't precisely at the energy that we need to ionize hydrogen. Many of them have a little bit more energy, and that energy gets carried away by the liberated electrons. And those electrons are going to bounce around and collide with a number of other electrons, and they're going to carry some energy with it. So this is going to work to effectively destroy the massive star's natal molecular cloud. So we'll see this beautiful H2 region, but it's really in the process of destroying that original molecular cloud. And that's going to make star formation a little bit less clustered and bursty. The other important effect is that it's kind of preheating the gas, so that when supernovae do explode, they're going to explode into this diffuse, relatively warm gas. And that's going to allow them to be a little bit more effective than if they encountered dense gas. So this preheating by photoionization is recently been shown to be quite important. All right, and last but not least, we have cosmic rays. So roughly 10% of a supernova's kinetic energy is believed to go into cosmic rays. Cosmic rays scatter off of magnetic inhomogeneities in the interstellar medium, and this can effectively transfer the cosmic ray momentum to the gas. Cosmic rays tend to make outflows a bit cooler and a bit smoother. We can see that in the simulation here. This is showing a little vertical slice of the interstellar medium in a simulation with and without cosmic rays. And there aren't very many differences at low scale heights, but at larger scale heights, we can see that there's a much smoother distribution of cool gas. There's still a lot of things we don't know about cosmic rays. We don't fully understand how they decay and what some of their transport mechanisms are. I encourage you to look at the thesis talk by Chad Bustard to see to learn some more about cosmic ray-driven outflows. All right, so to sum up, core collapse supernova, massive star winds, radiation pressure, photoheating, and cosmic rays all contribute to the feedback process on somewhat different temporal and spatial scales. So when we talk about feedback, we're really talking about all this stuff bundled together. So let's think now about how these feedback processes associated with individual stars can kind of work together to generate a galaxy scale wind. So the thing we need to remember is that the vast majority of the energy for feedback comes from the very short-lived massive stars and their supernova. So the effects of feedback are going to be largest when star formation is clustered in space and time. So let's look first at what happens on the scales of star clusters like the one we see here. So star clusters, because of their supernova and stellar winds, perhaps because of radiation pressure and photoheating, are going to create these little bubbles of hot gas around them. And here's our kind of textbook cartoon picture of this happening, where we have a little star cluster being born in the disk. It generates this bubble of hot gas. This bubble is going to expand along, where the density gradient allows it to, and it's eventually going to blow out of the disk. So this is our kind of cartoon image of what's happening. Now, I wanted to show you that reality is a little bit more complicated than this. So what I'm showing over here is a snapshot from the Tigris simulations. And I really wish I could show you the whole thing. I wasn't trusting my laptop to be up to the job of playing the simulation while also doing a Zoom. But I encourage you to go to the website below and look at these simulations because they're really impressive. What we're looking at here is a little slice through the ISM in a disk. And these simulations have very high resolution. They have a 3-phase interstellar medium. They're self-consistently treating star formation. So these little dots here represent star clusters, and size here shows mass, and color indicates the ages of these star clusters. The next slice over shows you the gas density. The next slice over shows you the gas temperature, the pressure, the velocity in the z direction, and the magnetic fields. And the main thing I want you to take away from this is that, our cartoon picture isn't quite applicable when we have a highly structured interstellar medium, and we have these little, bursts of star formation happening in clusters going off somewhat irregularly. So reality is pretty complicated. Okay, so let's get back to our question. Do all galaxies drive galactic winds? Well, when star formation surface densities are low, these superbubbles are going to break out of the disk, but they're going to be relatively isolated. And in this case, we think what we're going to see is something like a galactic fountain. So that's, so this nearby galaxy, NGC 891, is almost perfectly edge on. It's kind of a Milky Way mass galaxy, but it's somewhat less bulge dominated. And the thing we can really notice are these streamers of dust extending vertically. And I've overlaid a little snapshot of our simulation just to show you how some of these structures are kind of broadly similar. This is the density snapshot from our simulation. And we think that these are indications of these superbubbles kind of breaking out and venting some of their gas into the halo and dragging with it some of this cooler entrained material like dust. Now, it's likely that these individual superbubbles are going to break out. Maybe they'll entrain some more gas in the halo, but they're eventually going to fall back down onto the disk in what we call a galactic fountain. So this is a wind, but it's not really a wind in the sense that it's coming from the center of the galaxy. These are driven really from individual superbubbles. When star formation surface densities are much higher, the superbubbles begin to overlap, and then they can much more efficiently use that thermal energy from supernova and stellar winds to drive outflows. And this is what we see here in this galaxy where we're zooming in. This is, the red is from H alpha, the blue is from X-rays, and we're seeing this kind of multi-phase wind, this beautiful little bubble arising from the center of this galaxy. So do all galaxies drive galactic winds? Well, probably not. In the local universe, winds are primarily found in galaxies that are undergoing a starburst, so they have some kind of elevated star formation rate. For M82, the galaxy that we were just looking at, its starburst was probably triggered by its interaction with M83. But M83 is a lot more gas poor, it's a lot more massive, and it doesn't appear to be driving a wind. But we do see this wind coming from the center of M82. At high redshift, the situation is different. At redshifts greater than 1, normal galaxies have star formation surface densities comparable to the starburst in M82. And in these cases, we think that winds are probably ubiquitous. So again, in the local universe, winds are a phenomena that is really most appropriate to the galaxies with the highest star formation rates. At high redshift, normal galaxies are undoubtedly driving galactic winds. All right, let's take a closer look at M82. One of the things that makes M82 such a wonderful test case is that it's so close. So we were kind of cosmically lucky to have a starburst at a distance of only 3.6 megaparsecs. And this allows us to look at the wind physics in a lot more detail than we can with other galaxies. So to give you some context, M82 has a dynamical mass of about 10 to the 10. So it's really a dwarf galaxy. Nonetheless, it has a star formation rate about a factor of 10 higher than our Milky Way, and a star formation surface density that's more comparable to that of a high redshift galaxy. This color composite that I showed you at the very start of the talk, just to remind you, is showing optical light from the disk of the galaxy, seen edge on, X-rays shown in blue, and we're seeing cool entrained material in red here. And we'll look at each of these images. We're going to pull this apart and look at each of those phases individually. So first, we're going to take a look at that X-ray gas. So I'm going to try to sort of keep the same scale here, but I'm switching images, and color here now shows X-ray temperature. So in the center of this picture, we have hard X-rays coming from 10 to the 7 to 10 to the 8 Kelvin gas that is produced by the supernova and stellar winds in the starburst. And this is really the engine of the burst. At larger radii, we're seeing gas that's more like 1,000,000 degrees, and this is glowing in soft X-rays. And we're probably looking at the interface between the kind of adiabatically expanding hot wind and the cooler entrained gas. We don't have a direct measurement of the outflow velocity of the hot gas, but using some simple analytic arguments based on the temperature in the nucleus, we calculate that it's probably outflowing at a velocity of around 1,500 to 2,000 kilometers per second. So well above the galaxy's escape velocity. All right, now that first color composite I showed you, the red was showing this warm dust emission, actually coming from polycyclic aromatic hydrocarbons. This is from a Spitzer image. And that has a pretty similar morphology to gas that we see in H alpha. So this is warm ionized gas. And we think that this warm ionized gas is a combination of gas that's kind of photoionized by the starburst and shock ionized by this interaction with the hot gas. H alpha is, a pretty straightforward thing to observe. We can sit our spectrographs on this and measure velocities. After accounting for projection effects, we think that warm gas is moving at a velocity of about 600 kilometers per second. So again, probably enough to escape the galaxy. So we're going to keep going and add some new phases to this picture. So the background image in red is our warm dust emission, once again, but now what I'm showing in blue is neutral gas, H1, and the contours show some CO. And it turns out that even the neutral gas is outflowing here, although at a somewhat lower velocity. So all of this is just to emphasize that galactic winds are a highly multi-phase phenomena where we have, gas all the way from, millions of degrees or higher temperatures all the way down to gas at, tens of degrees that is dominated by CO. So galactic winds are truly multi-phase phenomena. This gives us lots of different ways to observe them, but we need to also keep in mind that any one phase of the gas probably isn't telling us the full story. So when we look at other nearby starbursts in the local universe, they have morphologies that are broadly similar to M82. This is a color composite made by Dave Strickland, showing X-rays in blue, H alpha in pink, and the disk of the galaxy is shown in green. And we can see this is M82, and these are some other relatively nearby starbursts. And they look pretty similar. We have this, central outflow of both warm and cool gas. But the trouble is that it's difficult to extend these studies outside of the local universe. Once we get beyond about 20 megaparsecs, it's just really hard to see this diffuse gas. So we need different techniques. And one that's proven to be particularly effective is absorption line spectroscopy. So we can aim our spectrograph at some bright background source. In this case, we're looking at a quasar, and look for absorption coming from that cool diffuse gas along the line of sight. So that's very useful to get information about, where that gas is and what the ionization structure it is. But if we want to understand the velocities, we need to modify this technique just a little bit, and we need to look down the barrel. So down the barrel observations refer to this idea of using the starburst itself as a backlight. So rather than looking at a quasar, we're looking at the starburst itself. We're going to see material between us and the starburst in that spectrum. So we kind of lose our radial information because we're going to see everything along the line of sight, but we can get information about gas velocities. Now, in this picture that I just showed you, our little cartoon, we were using Hubble. And the reason for that is that a lot of the cosmically abundant, or the resonance absorption lines of cosmically abundant ions are in the vacuum ultraviolet. The vacuum ultraviolet is a really great place to study galactic winds because we have transitions ranging from, oxygen 1 tracing neutral gas, all the way up to oxygen 6, which traces gas at almost 1,000,000 degrees Kelvin. So we have the ability to probe lots of different phases of the outflow. In the optical, we're a bit more limited because we only have calcium 2 and sodium 1. And both of these ions are particularly fragile. So we've learned some really important things by studying them, but we can't extend those studies to galaxies that aren't full of a lot of dust to shield these fragile ions. So the space UV is really where we want to be. All right, so let's pause for a minute and think about what some of the big questions are that observers would like to know. So now that we understand some of the observational techniques. One of the main things observers would really like to understand better is how galaxy outflow velocities depend on host galaxy properties. And one reason this is so important is this is a really direct manifestation of the feedback process. We're looking at outflow velocity, and we want to understand how that correlates with the galaxies themselves. And this is something that simulations can try to reproduce. Right now, a lot of simulations are tuned on things like the star formation density of the universe, which is impacted by feedback, but it's also impacted by a wide variety of other processes. So if we can develop some really nice correlations, our simulations can try to use these as benchmarks. We would also like to know how much gas galaxies eject in winds. That is really one of the fundamental questions. How efficient are they at removing mass from galaxies? And how far does this material get? Does this gas, ultimately come back? Can we eject gas out to the virial radius and beyond? So let's think a little bit about what we know about these three questions. I chose these three because I think they're three where we have preliminary answers, but our answers should get better in the very near future. So let's think about these down the barrel observations. So this shows some cross UV spectra of nearby starbursts. And what we're looking at here is velocity of the outflow relative to the galaxy itself. So the galaxy's ISM should be at V equals 0. And we see absorption at a wide range of negative velocities, meaning this is outflowing material. Now remember, we're only seeing one side of the disk because we're seeing that material in projection against this background starlight. So we're not seeing the far side of the disk. So that gives us an unambiguous interpretation of these negative velocities. Okay, so we see that these two ions look a little bit different in some cases. In other cases, they look nearly identical. This is silicon 2 and silicon 4. And we see that we can detect absorption all the way out to velocities of 400 or even higher kilometers per second. Now, we don't see a single velocity, right? Because we're looking sort of down the barrel here. We're seeing gas at a range of different radii, and we therefore see gas at a range of different velocities. So typically, we kind of parameterize the outflow velocity by looking at the maximum velocity, or we can look at the sort of average velocity. Both of those give us very similar results. So this is a plot of the maximum outflow velocity versus stellar mass and versus star formation rate. And we can see that there's a surprisingly tight correlation that's independent of galaxy morphological type. So even mergers sit on this correlation between stellar mass and outflow velocity. We see very similar correlations when we look to higher redshifts. So Kate Rubin has done some nice work at redshift of roughly 1/2 that shows some fairly similar trends. Now, if you had asked me what I thought the best trend was going to be, would be star formation rate divided by stellar mass. Because to me, I thought, star formation rate is what's pushing the gas out, and stellar mass is what's providing the potential well to hold the gas back. But it turns out that wasn't the best correlation that was seen. So I'm switching papers right now, but this paper includes much of the same data in the previous paper. So now we're looking at star formation rate divided by stellar mass as a function of maximum outflow velocity. And we can see that that's actually a pretty noisy correlation. So my intuition there was wrong. But what is a very tight correlation is star formation rate per unit area versus outflow velocity. And this probably reflects the fact that as those superbubbles overlap more and more, as the star formation rate per unit area gets higher, we're more efficient at extracting energy from the outflow, up to a certain point where perhaps this trend begins to level off. All right, well, let's turn to our mass outflow rates. So if we could know any one thing about a starburst, we would love to know how the mass outflow rate, what the mass outflow rates are relative to the star formation rate. For a given amount of star formation, how much gas is getting locked up into stars versus how much gas is going out in an outflow. So if we just did some dimensional analysis on the mass outflow rate, we could say, well, that's kind of proportional to the mass. If we think about the mass being, in a shell, we could think about that being proportional to the mass times the velocity divided by the radius. We can't measure mass directly, but we can measure the column density. If we knew what radius that stuff was at, that would give us the mass. So if we put all this together, we see that we expect our mass outflow rate to scale as the column density times the velocity times the radius. Now, velocity is relatively straightforward to measure from our down the barrel observations. Column density is for ions. With high resolution data, I can tell you what the silicon-2 column density is. What's a bit harder is knowing what the total gas column density is. We need to know something about the ionization corrections. And finally, the radius turns out to be a surprisingly hard piece of the puzzle. We don't have any information about where that gas is in our down the barrel observations. It could be very close to the nucleus. It could be quite far out in the halo. So I thought this problem was too hard to tackle, but I was proved wrong by my thesis student, John Chisholm, who's now beginning a faculty position at the University of Texas in Austin. So he decided that if we coupled these beautiful COS far UV spectra with cloudy photoionization models of all of these different ions, we could actually back out some information both about the ionization corrections and about the radius that this gas is at. So he did this, and here are the mass outflow rates from his work divided by the star formation rate, shown as a function of stellar mass. And this is a surprisingly strong and fairly tight trend. So this shows the data, and these are some results from a semi-analytic and a hydrodynamic simulation. And we can see that low mass galaxies are going to have far larger mass outflow rates by an order of magnitude or more than Milky Way mass galaxies for the same amount of star formation. The comparison between simulations and observations is insightful, but they're comparing slightly different things because we're only looking at the warm phase of the outflow, whereas the simulations are looking at all of the phases. But it's fairly encouraging for simulations that they're getting sort of close to the right slope from the observational data. Now, you might say this is a pretty important trend, but I see you only have 8 data points here. Yes, that's a big problem. We would like to measure this statistically. But we hope to be able to do this in the near future. So coming soon will be 45 galaxies with very high quality HST COS UV spectra from an HST treasury program led by Danielle Berg and John Chisholm, so called Classy. So keep your eyes out for that. All right, well, let's talk about our last observational question. How far do these galactic winds get? Can they reach the circumgalactic medium? So one way to approach this question is to use galaxies where we have some kind of background quasar that we can look at. And this enables us to probe quite large radii away from galaxies and to really understand whether that gas is being impacted by the outflow. But one of the things that makes studying circumgalactic gas difficult is that it can have a lot of different origins. A lot of the gas in the circumgalactic medium, in fact, the dominant fraction, probably comes from cosmological inflow. So we have to try to tease these things apart. And the way Heckman and collaborators did this was to look at a sample of galaxies that had a recent starburst in the nearby universe, and a sample of galaxies with more normal star formation rates. And this is what we're seeing here. We're looking at the carbon-4 equivalent width as a function of projected distance from the galaxy. And so we're looking at distance relative to the virial radius. So out here, this is 1.5 times the virial radius. And we can see that, in fact, the galaxies that have experienced a recent starburst are quite offset from those who haven't. And this suggests that the CGM is more metal-rich or maybe more stirred up in galaxies that have hosted recent starbursts, likely due to the impact of their galactic winds at large radii. All right, well, we'd like to have a real image of this wind-CGM interaction. So my collaborators and I set out to try to do that, and we wanted to focus on some of the most extreme starbursts in the universe. So we're working with a sample of roughly 50 ultra-compact starbursts at redshifts of about 1/2. And they're exceptional because their star formation is so compact. They're probably the relics of recent mergers. And because their outflow velocities are so high. So here we're plotting stellar mass versus outflow velocity. And the black and gray points are from John Chisholm's work at low redshift and Kate Rubin's work at redshift 1/2. And the red points are our sample of compact starbursts. And they really have pretty exceptional outflow velocities. But this is most likely due to the fact that they have incredibly high star formation surface densities. If we look at this trend in terms of star formation surface density, this may explain why they're such outliers. All right, well, we're just gonna focus in on one of these galaxies. And we named this galaxy Makani, which is Hawaiian for wind, and you'll see why in a minute. So what I'm gonna show you next is this same HST image, but overlaid on it is an image from the Keck Cosmic Web Imager that is an integral field unit spectrograph, and we're gonna take out a little slice focused on oxygen 2. So we're gonna look for oxygen 2 in the outskirts of this galaxy. And this is what we saw. So here's that same HST image that I showed you a minute ago. And here's the image taken in the light of oxygen 2. And color here just shows you the intensity of the oxygen 2. But what I want you to notice is this gigantic 100 kiloparsec nebula around this galaxy. That is most likely the result of this galaxy's high velocity outflow interacting with the circumgalactic medium. Now, just to give you a little bit of context, here is M82, and we can see that the CGM around M82, or the H alpha light around M82, shown in pink, really only extends about the same size scale as the disk. Whereas here, we're seeing, material that extends much, much farther than even these tidal tails reach. So we're beginning to be able to directly study that wind-CGM interaction. All right, I'm not going to have time to dwell on the current questions in theory. There are a lot of fascinating questions out there. One of them is what subgrid feedback prescriptions work best to reproduce observations. So simulations are simply not capable of resolving the relevant scales needed to, fully follow the evolution of a superbubble. These are sort of parsec scales. Most simulations that attempt to look at cosmological volumes can't resolve anything close to that. So they need to use a different prescription to put feedback into their simulation. Sometimes this is done by turning cooling off. Other times this is done by providing little kinetic kicks to particles that are near supernova. There are many different prescriptions, but they need to be tested against more data really directly focused on galactic winds.
Christy, I think you want to finish up pretty soon.
Okay, sorry about that. All right, so I'm not going to talk about these other theoretical questions, but let me just note that, let me just skip forward and talk about the future a little bit. So I think we're going to see a lot of progress in the future relating simulations and observations. Right now, observations are really focused on these absorption line profiles. We love our absorption line profiles. That's how we infer most of the physical properties of galactic winds, but we don't know some basic things, like is the gas that's moving fastest at small radius or large radius? We actually don't know that. Simulations, on the other hand, are great at producing maps of temperature and density and mass outflow rates, but they can't tell us much about what the individual ions are doing, at least not yet. There's some great work by Kim and Ostreicher to actually correctly follow the phases of the ISM and synthesize mock data. So this should really help us put these two pieces of the puzzle together. All right, looking forward to the future, maybe a few more years down the line, we're going to have extremely large telescopes. And their light gathering power can offer some significant advantages. Right now, we often study outflows by looking at a single line of sight. But with the power of these extremely large telescopes, we'll be able to look at fainter quasars, and we'll even be able to use background galaxies as our light sources. So that's going to lead to a lot of progress in our understanding of the CGM and outflows. Finally, even further down the line, in the mid-2030s, we're going to see the launch of the Athena X-ray Observatory. This is an ESA satellite, and it's going to carry a high-resolution imaging spectrometer that's really going to enable us to measure the temperature, density, and chemical content of the hot phase. And right now, we know a lot about this warm ionized phase. If we can add in the information about the hot phase, we'll have a much more complete picture of the feedback process. All right, well, let me just put up my summary there. I think the important point is that galactic winds are this really extreme manifestation of the feedback process. And by studying them, we really can hope to better constrain feedback itself and its impact on galaxy evolution. If I piqued your interest at all, I encourage you to look at a couple of these review articles. There's a lot of great information there. Thank you very much, and I hope to see you in Madison.
Great. Thank you so much, Christina. That was a wonderful talk, full of information. We have some time for questions, and I'm going to read them from the Q&A window. Feel free to add them. We're going to have to finish up in just a few minutes officially, but Christy has told me that she's happy to stick around and continue answering questions after we have, as it were, unofficially finished. So let's start with Neil Sharma writes, first of all, great talk, thank you. I've always wondered if this outflow of galactic winds and material can contribute to star, globular cluster, dwarf galaxy formation far from the parent body. Is it a possibility or proven occurrence? What is the furthest these galactic outflows can reach out?
Well, that's a multi-layered question.
Yes, there's like 6 questions.
Yes. So, you know, we're working on this question of how far winds really get. We think right now that they're on scales of, you know, maybe 100 or 200 kiloparsecs. Certainly, they might have an impact on dwarf galaxies in the neighborhood of the central galaxy. One of the things that we've learned from some simulations like Zach-Hafen simulations where we can actually do particle tracking is, in fact, it goes a little bit the other way around. As dwarf galaxies are accreted into larger galaxies, their outflows play a pretty large role in populating the circum-galactic medium. So a lot of that material that might otherwise sort of come back as a fountain flow ends up getting stripped off and joining the halo of the main galaxy. So it's clear that there's a lot of satellite host galaxy interaction going on, I guess I would say.
Okay, next question is from Steve Spangler. Could you comment on the information provided by radio continuum emission, synchrotron radiation, in galactic winds? This is an important component because it traces the relativistic electron population.
Yeah, so I'm not going to say a lot about that simply because it's not my area of expertise, but I will say that it is a very important component, especially as we move towards studying the impact of the relativistic population, cosmic rays. So as we get better gamma ray observations and as we get deeper radio continuum data, I think we're going to be able to say a lot more about the potential impact of cosmic ray driven winds. So it's certainly something I wish I'd been able to say a little bit more about.
Okay, this will be the last question on the official front, but again, people are welcome to stick around and continue chatting. Can you comment, this is from Christine Ye, can you comment on the scale of the impact of these winds on the warm-hot intergalactic medium?
Well, so I think when we're talking, yeah, okay, so we're talking about now even further out, right? And I think we just don't know at this stage. Certainly we see metals out in the wind, and so that tells us that, you know, they're getting there somehow, so outflows must clearly play some type of role. But I think at these very large scales, right now we're reliant on simulations, and we're not sure that simulations have all of the feedback processes, you know, perfectly well implemented at this stage. So yeah, I think that's TBD. We need more data.
Okay, so I'm going to just call this particular session to an end, but again, informally, you're welcome to stick around and continue chatting about these things by the Q&A window. Let me just thank Christy again for a wonderful talk. Thank everybody for attending the talk and the meeting. This is the last of the plenary talks. It's not the end of the meeting yet, and let me just remind you that there's an iPoster session that starts in just a few minutes that everyone is encouraged to attend. And then at 6:40 p.m. Eastern Time is the AAS members meeting, and you should have all meeting participants should have received an email this morning to link to that, and that can learn about the business events. That is a separate link from the main meeting link. So again, thank you, Christy. Thank you to the audience, and that will officially end the session. But again, feel free to continue chatting about all these good questions that are coming up.
All right, thank you. I will stop my screen share.
And Christy, you can see the questions themselves, right?
I am trying to look at the questions right now.
Click on Q&A.
All right, so chat Q&A. Okay.
The first few we already talked through, so right. But the order is a little funny, so
I think you're right.
just to confuse you.
Let's see. Excellent. We have a very good reference suggestion.
There's one question that you that because of the funny way that the order happens that you may not have seen, by William Waller, about outflow velocities as a function of distance from the host.
Yeah. So where do you see that one?
It's the third one,
okay,
currently.
The third one
From the top.
Okay, so this is a really good question. How do outflow velocities vary with distance from the host? And we wish we knew the answer to this. I think and I'm not sure there is one answer either. You know, we sort of, our simple models of the outflow are like a smooth shell of material heading out. When you see those simulations, you actually see that there's probably multiple different velocities at a given radius. But we would like to know, are outflows speeding up or slowing down? And you can imagine, you know, different scenarios. If this cool gas is accelerated by ram pressure, then we might expect it to be kind of continuously accelerated, and we would expect it to speed up with radius. If, on the other hand, you know, it's another way for producing this cool gas is probably if it's entrained in the hot flow and then it cools out of the hot flow. In this case, we might expect it to start out fast, but maybe it would slow down as it encountered more and more material in the circum-galactic medium. So we don't really know right now. In M82, in the H1 observations, we certainly do see a deceleration, but each phase might be doing things a little bit differently. So I think the situation right now is not very clear. I'm working on this problem by looking at galaxies that have this sample of ultra compact galaxies. They have very, very, bursts that are very isolated in time. So they give us a way of looking at the kind of temporal evolution of the starburst by looking at bursts that are at slightly different ages. So we see galaxies that are having ongoing starbursts, and we see some that are a few 100 million years post-burst. And those data actually suggest that the outflows are slowing down over time, but I'm not sure that's yet definitive. So this is still kind of unpublished work. So that's a really good question that I hope we'll be able to address one of these days. Let's see. Are jets from very young stars a contributor to galactic winds? So they certainly are a feedback source. I think they're probably subdominant to a lot of the sources that I mentioned, but they're actually included. I know the fire simulations include, young stellar jets as a potential feedback source. So I think that's a good question, and I can't answer it more quantitatively than that, but I think they are a contributor. Another question is, what is the role of magnetic fields on galactic winds? And I think that's going to be really important for these cosmic ray-driven winds. I wanted to show, I ended up cutting it out, but there's a beautiful Sophia image of the magnetic fields in M82. And I think that's a huge, it's an important thing to understand to better understand cosmic ray propagation. So if they end up being important, magnetic fields are going to be important. The other place that magnetic fields might matter is in helping protect this cold gas from being destroyed by the hot outflow. And I know there's been some work recently trying to simulate that and looking at how magnetic fields can help protect some of these cold clouds. I think the answer is probably not as completely as we hoped, but depending on whether that field is oriented parallel or transverse to the outflow, it can have some impact. The missing metals problem. That is a good problem. I'm not sure I have an answer to necessarily where those metals are. We have a good idea of the amount of metals that should be produced by the galaxy, of course, if we think we understand stellar yields. And the question is, where did they go? We see many of them in the CGM, but those metals are somewhat underabundant. And the question is, are they hiding in different phases that we're not yet able to observe really effectively? And yeah, I'm not sure about the missing metals problem. I think that's still a good open question. All right, let's see. Is the gas flowing out, which absorbs the UV rays, similar to gas absorbing X-ray? Let's see. So so if I'm skipping your question, it's because I probably don't have a good answer to it. So yeah, I think these are all good issues. There's this question about whether, we need to do time-dependent calculations of the photoionization, not assuming things are in thermal and statistical equilibrium. That might be very important for galactic winds, just because we have, we saw how complex and how multi-phase that whole process was. And it's not clear there's really enough time for all of these processes to be in equilibrium. And I think there's some great work that's been done on this with small scale simulations. So I think that is a pretty relevant issue. All right, I think these are all the questions that I probably have the ability to answer. So I think I'm gonna cut it off there, and thank you all very much for your interest. And I hope to see you in Madison one of these days soon. Thanks very much.